The chi-square distributions are a new family of distributions for us, again by degrees of freedom, so a different distribution for each number of degrees of freedom. For a chi-square test of association, the way we calculate degrees of freedom is based on the number of rows and the number of columns in our table. The table that we're looking at right now has degree held as our columns, and there are 3 of those: junior college, bachelor's, and graduate. So our number of columns would be 3. We're going to subtract 1 from that. Our rows are views about astrology, scientific or not scientific, so there are only 2 rows. We're going to subtract 1 from that also and do this product. 2 minus 1 is 1, 3 minus 1 is 2, so we have simply 1 times 2, or 2 degrees of freedom. That means that we would want to look at a chi-square distribution with 2 degrees of freedom. This chart here shows a few different chi-square distributions. The smallest degrees of freedom that we can see here is 5. So we can see the graph for 5 degrees of freedom. It has heavy right skew, and it does look like the smaller the degrees of freedom we have, the more skewed the distribution is. When we get all the way up to 15 degrees of freedom, we can see that it's starting to look a little bit more symmetric because the center is moving toward the right in the same direction as the tail. An interesting fact about these distributions is that the mean of the distribution is equal to the degrees of freedom. So for example, if I look at 5 degrees of freedom, I can see that if I find 5 on the horizontal axis here and trace up to the curve with 5 degrees of freedom, I have hit the approximate center of that distribution, meaning that roughly half of it is on the left and roughly half of it is on the right. As we know, that's really true of the median, not the mean. The mean would be slightly to the right of that point because this distribution has right skew, but it's only very slightly to the right, so that statement still is almost true. We can look at the other values of degrees of freedom here and see that that continues to hold. For 15 degrees of freedom, you can see that 15 is pretty much the center of that distribution. Another important fact to remember is that a larger chi-square test statistic means stronger evidence against the null hypothesis. Because of that, the way we use these distributions is to measure how far out in the tail we are. If I were to mark a chi-square test statistic for one of these distributions here, I would measure the strength of evidence by how much of the tail is even larger than that test statistic, which means that we always do a right tail for this particular test. There's no such thing as a two-tail test here. The alternative hypothesis is always two-sided because it's just that there is some association between the variables. It's not really possible to have a one-sided alternative hypothesis for this multiple comparison test because it's not a simple comparison of 2 parameters. So even though it is in some sense a neutral alternative hypothesis that doesn't favor one side or the other, we always do a right tail to find our p-value. So let's go ahead and find our p-value by first doing an estimate by hand. The conditions for using a chi-square distribution are that each expected count must be at least 5. Note that's the expected counts, not the observed counts. So we can't necessarily make this call just by looking at our table of data. We have to start the problem and find the expected counts before we can be sure whether the condition is met. If we look back at our table with the calculations, the expected counts here are the numbers that we calculated. 49.8, 122.2, 65.1, 32.9, 61.8, and 25.2. All of those are at least 5. And therefore, we can say that yes, the conditions are met. We also want to be prepared to explain exactly what we checked in order to make that designation. We already found our degrees of freedom. That was 2, right? 2 rows, 3 columns, so 2 minus 1 times 3 minus 1. And now here we're given a chi-square distribution with 2 degrees of freedom. And we're going to locate our chi-square test statistic. By the way, that was chi-square equals 3.6 from our prior calculations. We're going to locate that on the horizontal axis here. Chi-square equals 3.6. And based on the information we're given, we will estimate the tail area. So I can see that I'm filling in this right tail, and that it's clearly greater than 10% because 10% is the highest thing that's marked here. We want to come up with a rough estimate based on that. I can tell it doesn't look like quite double the area that's in that tail starting at 10%, so it's probably less than 20%. We might just ballpark estimate this at about 15% for a p-value of 0.15. Your estimate might be a bit different from mine, but I would say that anything between 0.1 and 0.2 is certainly considered reasonable as an estimate for this kind of problem. Now, the way that we write our conclusions is, at least in part, very similar to what we've done on previous tests. We can still describe the strength of the evidence based on the p-value. A p-value of 0.15 is just right about on the edge of what we might consider to be weak evidence or no evidence. So we could go with either of those answers here. I'm going to choose to say weak evidence for now. And we'll stay consistent with that as we write our conclusion. But no evidence would also be a reasonable answer here, because any higher than 0.15, and we would definitely go for no evidence. We're going to see how to write our conclusion in just a moment. Every multiple comparison test requires a two-part conclusion. Part 1 is what we were just describing. Is there statistically significant evidence of a difference in proportions or of an association between these variables? This is just based on the p-value. Or similarly, we could just describe the strength of the evidence if we're not given a significance level. So part 1 of our conclusion is most similar to what we are used to doing. We want to say that there is weak evidence, in this case, of an association between degree held and views about astrology. Remember that we're basically saying we have weak evidence in support of our alternative hypothesis, so we're going to fill in the words that we use to define our alternative hypothesis. Alright, so again, weak evidence is what we found based on the p-value, and in support of some association or an association between degree held and views about astrology, that is just writing out in words what HA, our alternative hypothesis, is. Now, for part 2, we want to see where the largest difference is observed, and to do that we need to find the largest contribution to chi-square. So we need to look back at our calculations and see which of those cells made the largest contribution. Recall that the cells that make the largest contribution to chi-square are also the ones that have expected and observed counts farthest apart. So looking at our calculations here, we saw that this calculation gave us the largest contribution to chi-square, and our second largest would be this one here with a contribution of 1.072. At the very least, we need to make sure we comment on the one that makes the largest contribution. If there are two that really stand out from the rest, I would recommend commenting on both of those. Now, we need to figure out what cells in the table these refer to. This one here was scientific and junior college, and this one over here was scientific and graduate degree. Now we need to comment on which table cells these came from, and we also need to make it clear whether the observed count is greater or less than the expected count. Since we're just looking at the computation here, we can pick those out by looking at the actual numbers we used in the formula and remembering what order they go in. This is observed, this is expected. So we have 27 as our observed count and 32.9 as our expected. Based on that, we can see we saw fewer than expected. And that makes sense. We saw fewer holders of a graduate degree thinking that astrology is scientific than our expected count. Over here in scientific and junior college, we can see our observed is 31, our expected is 25. So here we saw more than expected. Now part 2 of our conclusion has to capture all of this. We want to say which cells of the table made the largest contribution to chi-square, and we identify them by the actual categories, and also indicate whether we had more or fewer than expected in both of those cases. So we say that the largest contributions to chi-square are from these table cells. We have our junior college scientific. We need to identify both variables where we saw more than expected, and from graduate scientific in which we saw fewer than expected. So this is all telling the story that we would expect it to tell, which is that it looks like the higher the degree, the less people think of astrology as being scientific. And of course it's important to keep in mind that these degrees are not necessarily in the sciences, or else we might see a much stronger association. Looking at the whole table, we still only have weak evidence that there's any association at all.